we're going to talk a little bit about vision and optical instruments. Many of you have optical instruments and you don't think about it. They're called eyeglasses. Your eyeball is essentially, well, it's kind of like a ball. It's essentially 2 centimeters from the lens of your eye to your retina, which sits back here on the fovea. And in here in the middle, there's the vitreous humor. Your retina, well, your retina sits actually all over all of this, but this part is the most important part during the day. Um, you have a blind spot. There are various things you can do to find your blind spot. You normally don't notice your blind spot because you use the movement of your eye and your other eye to reconstruct what should be in the blind spot. But the blind spot is due to the area where the optic nerve comes in, and the optic nerve interrupts the retina at that point. There are various things that can go wrong with the eye. It can be unfocused because of it being too short, right? Or the eye being too long. So if your eye is too long, you're out of focus. If your lens is too strong, you're out of focus. Or if your lens is too weak, you're out of focus in a different way. Or if your eye is too short, you're out of focus in a different way. Um, Most people over 40 begin to experience some degree of hyperopia. That means that they are farsighted. You will notice when they try and read their phone, they hold it very far away from them. You will notice that when they're in the grocery store, they stand on the opposite side of the aisle from where they're actually looking because they can see better far away than they can up close. We do the various things to correct all of this with eyeglasses, um, and that's defined by a very simple equation, which is right here. All right, the power of your glasses is 1 over the focal length of your glasses. Now the focal length is the point at which, if you have lines coming in parallel like this, that your lens is going to make everything come down to a point. So the distance between the lens and that point is the focal length. Um, that relates to what you're seeing, the object, and so 1 over the distance to the object plus 1 over the distance to the image has to be equal to the focal length. What happens when you are farsighted? Right? When you're farsighted, this ends up being negative to make everything work the way it should, and so you'll have a negative diopter. Our 1 over f will be a negative number. Before I had my vision corrected via surgery, I was a minus 6.5 diopters in my right eye and a minus 6 in my left. Once you become farsighted, that becomes a positive number. And so when you go to the grocery store to find glasses to correct farsightedness with an over-the-counter pair of glasses, you'll see they come in plus 1 diopters, plus 1.5, plus 2, plus 2.5. While these may be okay-ish, those are pretty big steps. You still want to go to an optometrist to actually get a better prescription than you're going to get over the counter just by trying things on. All right, this is an equation we're going to play with, right? The other thing that's out there that we don't worry so much about in this class is the magnification. So magnification is the height of an image over the height of the object, or minus the distance of the image over the distance of an object. And you'll notice this minus sign means a lot of times the magnification is going to be negative. Well, what that really means in terms of seeing is you can kind of see in this picture, if you're looking at a tree that's way off in the distance, the image on your lens is upside down. Right? I mean, the image on your retina is upside down. And there's a cool experiment that was done once with some people that volunteered. They put on goggles that flipped the world upside down. Their brain learned to adjust to the world being upside down, and they started seeing things, reinterpreting the image as right side up. And then when they took off the goggles after a couple of weeks, the world was upside down, and it took them another couple of weeks to adjust to that again. All right. The way we see, there are 2 major things in our eyes on the retina that detect light. There are the rods. Rods are very sensitive. They can detect a few photons a second, which is not very bright light. They do not detect color at all. Your rods are responsible for your night vision. So when you're out at night in the moonlight and you can see in bright moonlight, but you don't see any color, that's because you're using your rods to see. The reason when you look at military equipment on the movies and helicopters in the movies that are flying around at night, the reason they use red, or if you come to the planetarium and you watch the screen at the back of the room during a show, it's all red. The reason we use red for exit signs and movies and things like that is because the rods do not respond to red. Therefore, the color red does not mess up your night vision. However, if you turn on your phone while you're out at night trying to see things, you're going to mess up your night vision for a good 20-30 minutes. It takes about 20-30 minutes for your rods, for your cones to get where they need to be, and for your rods, which are easy to saturate, for your rods to calm down enough to get into night vision. Our cones, in our cones there are three types. They come in red, green, and blue. That's why the primary colors are red, green, and blue, because that's how we see. If our cones came in blue, green, and yellow, those would be the primary colors. But they don't. They come in red, green, and blue. A really interesting thing about our color vision, if you read the ancient literature, the color blue does not occur in ancient Hebrew or ancient Greek or any of the ancient languages that we know. So it's not clear why the color blue doesn't occur. The Greeks, ancient Greeks, called the sky not blue, they called it gray. And they didn't call the sea blue, they called the sea wine dark. So it's not completely clear how long it's been since we started seeing the color blue. It may be that we've only started seeing the color blue in the last 2,000 years, which is pretty cool to think about. Wow, maybe there was a major change in that recently in history, right? Other things about vision and color, when you're looking at things that light is reflecting off of, what you're seeing is the light that did not get absorbed. This is why primary colors for a printer are different for primary colors for your eye, because printers are focusing on what light are we going to absorb, while your eye is focused on what light am I going to see. There are all kinds of different lights out there. They have different spectra, right? And so if you look at a standard incandescent has a spectra like this. The sun looks like that. You can buy, if you spend a little bit more money, you can buy fluorescent lights that mimic the sun a little bit better. But you can see here a standard incandescent, which, okay, maybe you guys are young enough, you haven't really seen many incandescents. But standard incandescent is much more red, has much more light down in the red and into the spectrum than a fluorescent light. And so standard incandescents tend to be warmer. We interpret them as warmer because they're more red, more yellow. Sunlight is a little flatter across the spectrum. You can spend some money and get some fluorescent lights that give you something much closer to the sun. A standard fluorescent light has these big peaks here and there, this big one down in blue, and then a big bulge here in red. But standard fluorescent lights end up looking much bluer than incandescents. Another thing about the way we see, seeing is not just a matter of the physical process of detecting the light. Our brain also processes everything to put it together into an image and interpret the signals that are coming together. Our brain actually puts together a three-dimensional image in our head and serves that up to the rest of our brain as this is what we're seeing. But keep in mind, you're actually seeing two different pictures, one with each eye. So your brain is constantly interpreting things. I'll show you, we're going to look here at an example of how your brain is interpreting things. Here, I'm going to tell you right now that square A and square B are actually exactly the same color. You're looking at that right now and you're saying Dr. Gerald is gone cray-cray because square A and square B are not exactly the same color. That's what you're saying to yourself right now. But what we have here is an image that tricks the software in your brain that's putting it together into making them look like they are different colors. Why? Your brain is constructing the shadow here and assigning different shades to make the shadow make sense to your brain. So here's what we're going to do. We're going to slowly cut out pieces of this image. All right, so I'm going to cut out pieces of the image. I'm going to cut out a little bit more. I'm going to cut out a little bit more. All right. Okay, A and B still look different. Cut out a little bit more. A and B still look different. Cut out a little bit more. A and B still look different, but they're kind of starting to look a little bit the same. And now I'm going to cut out everything else, and voila, A and B look exactly the same. Now you're going, all right, Dr. Gerald, you're just tricking us. This is not true. All right, here they look different. What you really did is you stuck in different squares at the end to make us think it looked the same. So we're going to go at this a little differently. Here's the picture again. This square over here that I have off to the side is exactly the same color as A and B. Now you're going, Dr. Gerald, nope, they aren't. You're kidding me again. Well, I'm going to just slide it over slowly until it touches both of them. And they are exactly the same. The way to see this, look at A. A doesn't change when it slips over and go down to B and it looks the same. Look at B. B doesn't change when it slips over. All right? Those two colors are exactly the same. Your brain simply puts them together differently, those two squares differently, to construct the shadow of this object sitting right here. One last thing on vision and how it goes wrong. This is what was wrong with the Hubble Space Telescope back before you were born. It had color aberrations, which meant blue focused at a different point than red. All right. Well, nope, sorry. It had spherical aberrations, which means depending on where you hit it, it focused at a different point. Spherical aberrations for the Hubble Space Telescope we fixed by going out and putting corrective lens in. These color aberrations we also can fix with corrective lenses. The two types of lens problems we typically have, though, that you're going to be worried about are myopia and hyperopia. Myopia, nearsightedness; hyperopia, farsightedness. And when you get to be 40, you get the joy of having both. All right, that's it for vision. The equations we're worried about on vision, there's really only one. The power of a lens is 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. Oh, did not mean to change that. Okay. Other things you want to think about, what is myopia? What is hyperopia? What are our primary colors? Why do we have the primary colors we have? And that will be it for vision.